So the general form of a regression equation, that's what we have just looked at. That is the general form of the regression equation. It is y hat equals a plus bx. And as you guys have already said, that looks very similar to y equals mx plus b. Now, I am possibly about to just blow your mind here. Are you ready? Did you know that y equals mx plus b can actually be written as y equals b plus mx?
Yes, that's possible.
Crazy, right? So like if you think back in algebra, like 2x plus 3 is the same as 3 plus 2x. Like it didn't matter which way you wrote it. We always seem to put it in mx plus b form, but it actually doesn't matter. So the cool thing is that you guys have already kind of seen this equation right here. Yes, the variables that we use in stats are slightly different. We use an A and a B instead of a B and an M. That's okay, but they mean the same thing. So if you were to use your context clues here, what do you think the A is for in our equation? That is our y-intercept. The A in this equation is the y-intercept. The reason that we like to put it first is because in stats, we're usually working with data. And the y-intercept is our starting point, right? In algebra, a lot of times when you would graph a line, you would put the y-intercept, and then you would do your slope from there. That's our starting point. So this is going to usually be our starting value in our data. So that's why we like to use it as the first. That's why we like to put it first. Okay, again with the context clues, the m is the coefficient of the x. So what do you think the b is in this equation? That's the slope. Very good. All right, so since you guys were in middle school, you've been told that m is slope and b is y-intercept. And now I'm telling you that b is slope and a is y-intercept. You know what? I don't want you to worry about that. Here's the deal. You guys are very rarely going to see this a and this b because most of the time you're going to see the numbers that are in the equation. So you don't need to get hung up on the fact that it's an A or a B or an M or whatever. Just recognize that the slope is in front of the x and the y-intercept is the number by itself. Just like it's always been, okay? Don't get hung up on the A and the B. Got it? Boy, enthusiastic today, aren't we? Y'all are rethinking that decision from yesterday, aren't you?
Yes.
Yeah. Figured. All right, here we go. What is the difference between y and y hat? Why does y have such a hat on it? What is the purpose? So y, when you actually use y, when you were using y equals mx plus b, you were talking about values that were on a particular line, and every value was on that line. So y is the actual y value for a data point. Y is the actual y value for a data point. When you have a scatter plot and you have all the little dots, every single dot has an x and a y value. That's how we know where to put the dot, right? We go to the x, we go to the y, we put a dot there. This is the y value for the data point. That's what y is. Y hat is the predicted y value from the regression equation. All, and I mean all y hat values are on regression line. all y hat values are on the regression line.
Nice.
So that's y hat. That's your format of your equation. We're going to work with that in just a second. All good? Okay. So real quick, I want to talk about the interpretation of slope and y-intercept. So I have the slope and the y-intercept. I said that right. So I have good news and bad news. The good news is that this class is not as math heavy as most math classes.
Yeah.
We don't do as much math in here as we do in some other math classes. Here's the bad news. We do a lot more interpreting, and when you interpret something, that usually requires a sentence. That's the bad news. Okay? So, you guys got a green piece of paper yesterday. At the top it says interpretations. These are all of the interpretations that we are going to get the opportunity to do.
It's just like this. Wait, all y values are blank.
I'm sorry?
Wait, all y values.
So these are some of the formats of the sentences for our interpretations. When we interpret stats, there's usually a general format that we use. Now there can be some slight, you can kind of move a word over here or over there or whatever, but the idea behind it needs to be the same. So here's some interpretations that are going to be very helpful in our class. The first one we did a long time ago, when you see the phrase describe the distribution and you have a single quantitative variable, you should use SOCS. What does SOCS stand for?
Shape, outlier, center, spread.
Awesome. And then we talked about the other day that when we see a scatter plot and we have two quantitative variables, that we might need to describe that distribution, and we would have to use SOFA. And what does SOFA stand for?
Signed outliers form association.
Yay! All right, and then we talked a couple days ago about correlation, the R value, correlation coefficient. And here's kind of how you interpret it within a general sentence. This one you can really mix up quite a bit. But basically, the correlation of whatever the value is. So the other day we had the example of negative 0.632 for the height and the steps per inch, okay? The correlation of negative 0.632 between, here you're going to put in the explanatory variable. Like what is the explanatory variable? So for the example the other day, it would be height. And then you're going to put in the response variable, the y variable, steps per inch, is, and then you would say, what is it? Is it weak, moderate, strong, or perfectly linear? Well, it was moderate for our example. And it had a negative association. Now, I don't remember how we wrote it in this class. We may have said there is a negative, moderate association between height and whatever. That's perfectly fine. Again, this one, you just got to make sure you include all of the things, okay? All right, here's slope. Here we go. For the slope, here's how you're going to interpret slope. For every increase of 1 in the x variable, the predicted y variable will either increase or decrease, depends on the sign of the slope, by whatever the slope value is. So I just want to point out here that you're only writing what's underlined for each increase of 1 in the x variable. The predicted y variable will either increase or decrease by that amount. So you're inserting, so it looks longer than it really is. So I don't want you guys to get too hung up on the fact that this looks really long. That's going to be for our slope. For our y-intercept, when the explanatory variable is equal to 0, the predicted response variable will be blank, whatever y-intercept happens to be, okay? So that's the interpretation sentences for your slope and your y-intercept. We'll get to these other ones here in just a little bit. Cool? Cool. We're going to put this into an actual problem so that it now might make some sense, because right now it's just a bunch of words. All right, so let's do that. You could say by writing a sentence and see green sheet. Yes. If you wanted to put that right here, how do you interpret the slope and the y-intercept of a regression line? Write a sentence, use green sheet. That would be perfect. And like I said, we're going to do an example right now. It's just kind of hard to do it when you don't have numbers and stuff. It doesn't make as much sense. So we're going to make sure we have sense now.
It's nonsense.
Have you guys ever opened a can of soda and it spewed out at you?
Yes.
Don't you love that?
No.
Isn't that fun? So some statistics students, Carrie and Danielle, they wanted to investigate if there was a way to keep that from happening. Have you guys ever heard of a way that you could keep it from happening?
Yeah. By not shaking it.
Don't shake it. That's one thing. Yeah, so have you ever tried to tap the top of the can like this for a couple seconds and then you open it and it's fine, right? So does that actually work? That's what they want to know. So for their experiment, they vigorously shook 40 cans of soda. They wanted to be extra on this. They randomly assigned each can to be tapped for either 0 seconds, 4 seconds, 8 seconds, or 12 seconds. So since they were tapping a certain number of seconds every time, that's why these are lined up like this. They just didn't happen to do 1, 2, or 3, 5, 6, or 7. That's why there's these spaces in this graph. Then they opened the can and they measured the amount of soda left in the can. Okay? Here's the scatter plot, and then here's the equation of this regression line that is on this scatter plot. This is the equation. So we have soda hat, that's how I would read that, soda hat, okay? Now that's your y variable, so that's your y hat, soda hat is y. 248.6 plus 2.63 times the tapping time, and that's our x variable. It is very common to write the variable name instead of writing the x and the y. It's just that way you don't have to wonder what is x and what is y. So that's pretty common. All right, so here's what we need to do, you guys. We need to predict the amount of soda that would be remaining if we tapped a can for 10 seconds, which they didn't actually do in their experiment. We want to predict, what if I just did it for 10 seconds? How much soda would be left? Is there any way that I could use this graph in order to find that answer? Yes, Rahul?
By using the equation.
So we are going to use the equation, but that's our second way to do it. Is there any way to do it from this graph?
By thinking logically where it would be on the line.
Good. So if I look at where 10 is on seconds, 10 seconds, and I go up to the line, about how much soda would be left over? 275. Okay, good. So that's how I can do it if I can use the graph. But if I don't have the graph and I only have the equation, I would need to use the equation. So what am I going to do with this equation?
Use it
I am. And how am I going to use it, Rahul?
by plugging in 10.
Good. I'm going to plug in 10 for the tapping time. So soda hat equals 248.6 plus 2.63 times 10. Soda hat equals 248.6 plus 2.63 times 10. And we just need to plug that into a calculator and figure out what that equals. It should be somewhere close to 275. Obviously, we looked at our graph and we saw it's close to 275. Should be close to that. And what'd you get? Okay, it's really close to 275, okay? 274.9 milliliters. Do you guys have any questions on how to predict that value?
specifics.
I would do one or two significant figures.
Okay.
Yes. All right, cool. Now we're going to do another example. Predict the amount remaining for a can that has been tapped for 60 seconds. Because who doesn't have a whole minute to tap their soda before they drink it, right? So we're going to tap for 60 seconds. Can I use the graph on this one?
No.
Why not?
Because it doesn't show 60 seconds.
It doesn't go that far. So I have to use the equation. Let's use the equation. Soda hat equals 248.6 plus 2.63 times 60.
406.4.
Wow, okay then. We got an answer already. 406.4 milliliters. How confident are you guys in that prediction? Very confident, right? We did the same thing for this that we did for the 10 seconds of tapping, right? What's the matter, Maddie?
Well, can of soda, can it be filled with 106.4
Oh,
milliliters?
I wonder how much soda a can even has in it.
Specify.
How many milliliters are in a 12-ounce can?
354.88 milliliters.
No.
You guys, there's only 355 milliliters in a can.
Okay, well, Susie's not gonna buy 40 water.
You guys, you know what that means? That means that if we tap long enough, we can create soda. We're not mathematicians, we are mathemagicians.
And also scientists.
Yes! You guys, this is exciting. We can actually create soda here by just tapping long enough.
Can we do that right now?
Wouldn't an exponential line work better?
There is only 355 milliliters in a can. This is a problem, you guys. What did we do wrong?
Math.
We did not do our math wrong. That's not true. We did our math absolutely perfect. But what did we do wrong? I'm gonna tell you guys what we did wrong here in just a few minutes, okay? And it's not your fault. Also, I know what you're thinking. How the heck am I supposed to know that there's 355 milliliters of soda in a can? Huh? What if this was on a test? And you do not phone a friend on a test?
Well, they didn't give us the appropriate amount of information to solve the question.
That's exactly right, Maddie. Maddie says we didn't really have the appropriate information to answer this question. We only had data that went from 0 to 12 seconds, and that's exactly what the problem is. And I'm going to give you guys a fancy name for that in just a few minutes. All right, real quick, before we move on, let's talk about the interpretation of the slope and the y-intercept. So if you look at this equation, which value is the slope?
The line.
Yeah, 248.
Slope. Where's the slope?
2.63.
The slope is with the x, right? mx plus b, slope is with the x. This is the x. So this is our slope right here. So we're going to interpret that. Now, just kind of side note, if we were in algebra right now and we did 2x plus 3, what's the slope of that equation? 2. What's the rise over run for that?
2 over 1.
2 over 1. So here's the deal, you guys. If we're using decimals and our value is 2.63, that's our rise. And what's our run? 1. It's always 1. In stats, since we prefer to use the decimal version, our run is always going to be 1. And that's why our slope interpretation starts this way every time. For every increase of 1, and then here's where I'm going to insert the explanatory variable, the x variable. For every increase of 1 second of tapping time, So all I've said there, guys, is every time I have a run of 1, okay, so I'm running 1. For every increase of 1 second of tapping time, the predicted soda remaining will what? Is my amount of soda remaining going to increase or decrease? How do you know it's going to increase? You're right. It's a positive correlation. The slope is positive. We have a positive graph. We have a positive correlate. All the things are positive. So we're going to increase by 2.63 milliliters. So you got a can that's been shaken vigorously for 40 seconds. Is it worth the extra second to tap a little bit longer to get 2.63 milliliters of soda remaining per second? I mean, I guess, sure. Now, at some point, you're going to hit a maximum. At some point, you're only going to have 355 milliliters of soda. Yes, sir.
What?
Are you just...
Oh, yeah, I was going to ask a question.
I'm ready.
Are they measuring, like, how much is coming out of the can?
They're measuring the amount remaining in the can.
Then how would it not decrease? Because it's leaving the can the longer we have it.
So the longer they tap on it, the more soda they're saving from exploding.
Never mind.
All right, cool. The y-intercept. Yes. The y-intercept. Here's the y-intercept. When tapping time equals 0, so all I said there was when x is 0. Remember, guys, when you're on the y-intercept, x is always 0 on the y-intercept, okay? So when tapping time equals 0, the predicted soda remaining will be 248.6 milliliters. So guys, here's the deal. Can has been shaken for 40 seconds vigorously. Handed to you. You immediately open it. Guess what? You just went from 355 milliliters of soda to 248.6, and you got about 110 milliliters of soda on you.
That's good.
That's a lot of soda on you. You are now a sticky mess. So, when the tapping time is 0, you did not tap on it, you just opened it. The predicted soda remaining is going to go to 248.6. That means you got soda all over you. You should tap.
Tap in.
Is it worth the tap though?
It's worth the tap. All right, cool. Everybody good? Perfect. All right, let's talk about this situation that just happened a few minutes ago. It is that word. What is that word?
Extrapolation.
When it happens, but it doesn't.
Extrapolation. Extrapolation. What is extrapolation? It's taking something out of context, basically. Here's an example of extrapolation with McKinney Boyd High School football team.
They think they're good, but they're really not.
That's not extrapolation, Raul. That's your opinion, and it's wrong. All right, here's extrapolation. The McKinney Boyd High School football team is undefeated. Therefore, we will win the NFL Super Bowl.
There you go.
I just took our football team out of context of what they are going to be able to do. I love our McKinney Boyd High School Broncos with all my heart, and I love watching them play, and I am excited that we will be 5-0 tonight.
Yeah.
But they're not going to win the Super Bowl of the NFL.
Against a bunch of grown men.
Okay, so that's extrapolation. It's basically taking something out of context. Now, what happened with our problem is we took it out of the context of the experiment from 0 to 12 seconds, and we went out of context all the way up to 60 seconds. That's a problem. And what was the problem? We created soda. That we can't do. So, extrapolation. Here's the official math definition of extrapolation. It is using a regression line outside the domain. Oh no, another mathy word. What does domain mean? X. Using a regression line outside the domain used to create the line. Now, could I use that regression line to predict what would happen if I tapped on the can for 14 seconds?
Yes.
Probably. But once I start getting 20, 25, 30 seconds, I'm starting to get a little risky. Okay? I'm starting to get to a point where it might not be a good idea to do that. So is it a good idea to extrapolate and take things out of context? No. Why not? The news does it all the time. No. Now, why? Why is this a bad idea? Here's why this is a bad idea. This is what we saw. And this basically goes to what Jack was saying. This is what we saw. Okay? But here's what happened. Our graph leveled off. We only saw a section of the graph. There are some graphs that they look linear in one section, and guess what? They actually curve. Or maybe they go up even more. The graph can do a lot of different things. So here's the deal with extrapolation. We cannot guarantee that the linear pattern continues. All right? So don't assume that the linear pattern is going to continue unless you verify that it does. And the only way to verify that is to get more data at that level. Okay? Any questions? Well, awesome then. All right, we're going to switch gears. You guys ready to switch gears? Which gear you want to go to? First? Which one? You want to reverse? Reverse. Okay, never mind. All right, here's what we're going to do. We're going to talk about something called a residual. When I say the word residual, what's the first thing that pops into your head? Leftover. What's the matter, Hayden? Residue.
Like residue, like sticky.
You know, you got some sticky residue. It's left over on your feet. Oh, you know what the worst residue is? The worst residue is Cheeto residue. Can we just be honest about this? Cheeto residue is the worst, right? Because Raul, how do you get it off? You got to scrape it on your teeth. And guess what you just did? You just scraped skin on your teeth.
Or you just wash your hands.
Why would you do that? Then you don't get the Cheeto residue. Takis is pretty bad too.
Sticky people residue.
So here's what residual is.
Syrup is the worst.
It is the leftover. It is the leftover value when comparing the actual Y value to the predicted Y value for the same X value. Excuse me, Miss Lake, you say what? So here's what I just said by writing this sentence about residual. The leftover value when comparing the actual Y value to the predicted Y value for the same X value. Every data point has an X and a Y value. Again, that's how we plot the point on the scatter plot. We go to X, we go to Y, boom, there's our point. We can get a prediction for that same X value similar to how we got the prediction for the 10 seconds of tapping time. We go to 10 seconds or whatever that is and we look at and see what the prediction would be on the line, or we plug it into the equation. A residual is what is the difference between the actual data point and the prediction for that same x value. That's what a residual is, okay? There's a formula for it.
Good.
You guys like formulas? This one's a really tough one. Resid. Oh, by the way, there is no fancy notation for residual. It's just resid. Resid equals, all right, hold on to your hats, your Y hats, your everything hats. Y minus Y hat.
That's so simple.
That's a tough one.
Ow.
This is your actual Y value minus your predicted Y value. This is your actual Y minus your predicted Y. Subtraction. Love that. Love that subtraction guy. Does the order matter in subtraction?
Yes.
It does. So do you have to have actual minus predicted?
Yes.
You do. How are you going to remember which one goes first?
By looking at your formula.
By looking at your formula. What if the formula is not in front of you?
Use your
A is
brain.
before P.
A is before P. I love that. It's alphabetical. Also, what class is this?
AP.
AP Stats. You guys, these are AP residuals.
On the test question, can you hit A dash P?
Yeah, sure, okay. Here's an AP residual question, you guys. All right, now how do I interpret a residual? This is on your interpretation sheet. You'll notice there's no italicized words. That's because there's not like really a format, but I am going to tell you guys how this kind of works. So if your residual is greater than 0, so if you have a positive residual, that means when you took the actual Y value and you subtracted the predicted Y value, that you got a positive number. Which number was bigger, the actual or the predicted? The actual. And the actual Y value came from the data point, the dot. That means the dot is above the regression line. That means the data value is above the regression line. The data point is above the regression line. Nice. What do you guys think is true if the residual is less than 0?
Below.
If the resid is less than 0,
Below.
the data point is below the regression line. Cool. Are those my only two options for residuals?
No.
What else could happen? What if I get a residual of 0? What does that mean happened?
It's on the line.
The data point is right on the regression line. If the residual equals 0, the data point is on the regression line. You guys are so smart.
Obviously.
Literally best class ever.
I mean, we have brains. We're not dumb people.